All right, we are going to be taking a look at Unit 2, Topic 6 on resonance structures and formal charge. We will take a look at using formal charge and resonance in order to draw Lewis dot structures of covalent compounds. So we're going to take what we've learned so far and extend it into what are called resonance structures. All right, we're going to start with resonance structures. So it says some structures, when drawn, will have the opportunity to have a double or triple bond appear in multiple places. And this leads to the ability to draw different structures for the same chemical. So we can see this example here of the nitrite ion, NO2-. So we can see two structures drawn. Both of them have the nitrogen in the center, oxygens on each side, but we can see that the one on the left has a double bond on the second oxygen, and the one on the right has a double bond on the first oxygen. So first, let's just take a look at how they arrived at one of these structures. So the nitrite ion, nitrogen has 5 valence electrons. Each oxygen has 6 valence electrons, so that would give us 12. And then it has a negative charge, so it gives us an extra electron. So that gives us a total of 18 electrons. So if I were to start drawing, I'd put my nitrogen in the middle and single bond my oxygens. And then that would use up 4 electrons. So then we'd have 14 left. We'd add our lone pairs on each of the oxygens. I'm just going to do some circles here. And that would use up 12 electrons, leaving us 2 left, which would go on our central atom, nitrogen. Now at this point, we can see that our nitrogen only has 6 electrons. It doesn't have an octet. So that's when we would use a lone pair and move it and share it with nitrogen. So I'm going to erase that and go ahead and share a lone pair with nitrogen. This is a ion, so we put it in brackets with the charge. So this is how we got the structure, the second structure down here, right? Now, we could have just as easily done the double bond on the right oxygen instead of the one on the left. So we could have, instead of moving this lone pair that was here, we could have chosen one of the ones on the right and shared the electron. So that's how we get the structure that's on the left down here. So we get two possible structures. So when we draw a resonance structure, we do have a couple of rules. We create the dot structure using the same rules as before. Nothing changed. If a multiple bond may appear in more than one place, then we draw each option. We draw all the options. We can only move electrons, not atoms. So to create my second dot structure, I would just put my double bond on the other side and make sure I had my octets around each atom. Now, it's not that one of these structures is correct and the other one is wrong. And really, it's not that either of these structures is correct. What's correct, what the actual behavior of the electrons and the atoms is that the electrons are moving. And it's not one structure or the other, it's both of them. It is an average between the two structures. So that's why we get this double-sided arrow that's placed in between them, because it's really not one or the other, it's both that are averaged. And how do we know this? We know this because we measure bond length. If we've already seen that a double bond is going to be shorter than a single bond, okay, that single bond is going to be longer. So if we were to measure the bonds, if they actually measure these bond lengths in this chemical, what they find is that it's not the length of a single nitrogen-oxygen bond or the length of a double nitrogen-oxygen bond. What they find through research is that it's somewhere in between. It's like a 1.5 bond length. So that tells us the electrons are not behaving as a single bond or a double bond. They're behaving as something in the middle, some sort of average. Well, it's really hard to draw an average of two structures. So instead of that, we draw both possible structures and put this double arrow in between to show that it's going between them or it's somewhere in the middle. All right? So here's a couple of examples. Ozone is O3. This is called ozone. You're probably familiar and heard it before, our ozone layer. So O3, each oxygen has 6 valence electrons, so 6 times 3 would give us 18 electrons to work with. And we're going to go ahead and have one of our oxygens be the central atom, and then 2 of the oxygens be on the outside, and we single bond them. So that's uses 4 electrons, so we've got 14 left over. Then we follow our same steps. We're going to add lone pairs to our outside atoms. So that's 2, 4, 6, 8, 10, 12. So now we have 2 electrons left. So we put those electrons on our central atom. And then the last step of our process is to check for an octet. So our outside oxygens are happy with their octet, but the central atom only has 6 electrons. So then we need to move a lone pair. Well, you can already see that we've got matching atoms on both sides. So if I move a lone pair, say, from the left oxygen and create a double bond, I could just as easily move it on the right side and create a double bond. Well, I'm going to go ahead and do the one on the left, create my double bond. So this is the structure of ozone. But because I could have picked either oxygen, either end to draw my structure, that means that there's 2 options. So what I'm going to go ahead and do is basically create the mirror image of that. Okay, I'm going to have my double bond on the right side, which means this oxygen on the right only needs 2 lone pairs. And my single bond on the left, which means this oxygen needs 6 lone pairs. And my central oxygen has its 1 lone pair and its 3 bonds. So those 2 structures together create ozone. And remember, it's not one structure or the other, it is an average. So if we talked about the length of the bonds, it wouldn't be a single or a double bond length, it would be like a 1.5. Now let's take a look at the carbonate ion. So some of our polyatomic ions are good candidates for this. This is carbonate. Should be familiar with that one. And then let's count up our electrons. So we've got 4 from carbon, 6 from oxygen, but there are 3 oxygen atoms. And then we're going to add 2 more electrons for that -2 charge. So we've got 6 times 3 is 18, 19, 20, 21, 22, 23, 24, 24 electrons to work with. All right, I'm going to start with my carbon, single bond my 3 oxygens to it. That uses 6 electrons, so now we've got 18 left. We're going to add the lone pairs to the outside atoms. So we're going to add 6 more dots to each oxygen to give it an octet. And at that point, each one got 6. There's 3 oxygens, so that's 18 electrons. So we've used all of our electrons at this point. So now we can check our octet. Carbon does not have its 8 electrons, so we're going to have to move a pair and share a pair between carbon and oxygen. So if I picked a pair from this first oxygen on the left and move it to be shared with carbon, I'm going to erase those electrons over on that side and fix my bond because that looks a mess. There we go. We get that carbon double bond. That carbon is now happy. It's got its 8 electrons, its 4 bonds, and the oxygens are good. So you can also tell that these oxygens, we've talked about before, the honk bonding, and this doesn't quite follow it, right? Oxygen really wants 2 bonds, right? Carbon's happy with its 4, but oxygen typically wants 2 bonds. Well, remember that we added 2 electrons to this, so that kind of fills in those extra 2 oxygens and gives them their electrons that they need to be happy. So this whole thing has a 2- charge. But remember, we're drawing resonance structures. So we could have just as easily put that double bond on the top or on the right side. So that means we're going to have 3 structures for this carbonate ion. So I'm just going to move my double bond to the top and single bond my other oxygens and then add their electrons. So if I've got a single bond, that means I need 6 electrons around it. to get me my 8. And my oxygen on top, I just need 2 more lone pairs to give me my 8. And it's an ion, so we put it in brackets and we put that charge. And then our last structure, we're going to put that double bond on the right side and give that oxygen its 2 lone pairs. Single bond our other 2 oxygens and give them their other 6 electrons. There's 3 lone pairs. And all this has a 2- charge. So carbonate can have 3 resonance structures, okay? Because there's 3 possible places to put our double bond. And remember, it's not that one of these structures is correct, it's all 3 of them together averaging. So our bond length would lie between a single and a double, an average between those. All right, hopefully this is starting to make sense. The only thing we're moving is electrons. We're only moving those double bonds around or triple bonds. So we're going to take a look at some more. All right, let's take a look at another example with CH3COO. So this is the acetate ion. And we also might recognize it written like this. So it can be written either way, and this first way that it's written gives you a hint as to how to actually draw it. So it can be helpful. So first let's get our number of electrons. So we have 4 from carbon, 3 from our hydrogens, 4 from the next carbon, and then 6 from each of the oxygens, so that's 12. Oops. And then we also have a negative charge that adds an extra electron. So 4, 3 is 7, 11, and 12 is 23, plus 1 is 24 electrons. So the way that it's written can help us draw it. So I'm going to show you how that works. We've got a carbon, and then I'm going to go ahead and follow what's next. It has 3 hydrogens attached to it. That one's so weird. So I'm going to add those 3 hydrogens, going ahead and single bonding them because we know hydrogen can only do that. I'm going to then add the next carbon, and then there's 2 oxygens, and they're written separately from each other. This is to help us understand that each of those oxygens is bonded to carbon. So at this point, we've laid out all our atoms and went ahead and single bonded them. So we've used 1, 2, 3, 4, 5, 6 single bonds. So that's 12 electrons. So we have 12 left. And following our steps, we would go ahead and finish the octet using lone pairs on our outside atoms. Well, the only atoms that need extra lone pairs would be the oxygens. So we can add 3 pairs onto each oxygen. Sorry, these look such a mess. And that would finish out each oxygen's octet, and that would use up the last 12 electrons. So at this point, we would check, the next thing would be to check our octet on our central atoms. So carbon on the left has 4 bonds, so that's 8 electrons. The carbon on the right with the 2 oxygens only has 3 bonds, so it's only 6 electrons. So it does not have an octet right now. So that means that we want to move a pair of electrons and create a double bond. Well, at this point, we might start to see that we have a resonance structure here. So you can see that, hey, if I move like 1 pair from this oxygen on the right and make a double bond, then I can create that octet for carbon and finish my structure. And this would give us our acetate ion. But we could have moved that lone pair from the top oxygen instead and gotten something like this, where we get that double bond on the top oxygen. So instead of just drawing one of those structures, we draw both, making sure that we give each of those oxygens still their octet with their proper number of lone pairs, and then giving it its charge for that ion. The last thing we would do is add that double arrow in the middle between the 2 structures to show that it's not one of the structures, it's not the other structure, but it's an average between the 2. And that would give us our 2 examples of acetate. So how do we know that this occurs? How do we know that there's not a single bond and a double bond? Well, we know that because when they measure the bond length between our carbons and oxygens, we don't find a single and a double bond, we find two equal bonds that are each an average between a single and a double. So that is our example for acetate. So I've talked about this already, but I want to make sure it's written down in your notes as well. So bond length is determined by the type of bond, single, double, or triple, and the elements involved in bonding, as we've seen in our previous sections in this unit. We know that the shorter the bond length, the stronger the bond, so it takes more energy to break a stronger bond. And since resonant structures can have more than one place where a double or triple bond may appear, the bond length is judged a little different. Neither of the structures below, we've got our NO2 molecule down here, can have, where are we at? Neither of the structures below is the true structure of the compound NO2 minus. They average together to form the actual structure. So instead of saying it has a single and a double bond, it is actually an average of a single and a double bond, sort of like a 1.5 bond. Therefore, the bond length is shorter than a single bond and longer than a double bond. And both NO bonds are the same length. Okay, so this here, this stuff is talking about is kind of proof, not kind of, it is proof that we have resonant structures. So we know these exist. We know that a chemical doesn't have just a single and just a double bond because we measure the bond length and see that they're the same on both sides. It's not a long and a short one, it's the same bond length. So that tells us that the bonds have to be the same. That is our evidence for resonant structures. So let's take a look at our next part. All right, we're going to take a look at an example of a multiple choice question. So the diagram shows the two resonant structures for a molecule of C6H6. The phenomenon shown in the diagram best supports which of the following claims about bonding in C6H6. So the phenomenon that's really being shown here is that we have resonance structures. We have two different structures drawn with that arrow in between. So we need to remember our ideas that surround this type of phenomenon. Well, we know that both of the chemicals, there's two possible drawings for the substance. The only thing that's different is the location of our double and single bonds. So we can see they kind of rotate around the circle. And the other thing we need to remember is that those bonds, the double and single bonds, are not actually double and single. They're actually all the same bond length. It is an average between these two pictures. So take a minute and look at the answers and see which one might fit that. Pause for a second and then we'll check it. So hopefully you came to the conclusion that answer C was our best option. All the bonds between the carbon atoms have the same length. So let's talk about some of these and why they're not good answers. Letter A talks about because of variable bonding between carbon atoms, or the variability between the bond in the carbon atoms, it makes it a good conductor of electricity. Well, covalent compounds are never going to be good conductors. Never good conductors. Metallic substances can conduct electricity. Ionic can conduct when they're melted or when they're dissolved, but covalent will never conduct electricity. So that's a big one we can cross out. Letter B, the bonds between carbon atoms and C6H6 are unstable and the compound decomposes quickly. Well, this resonance structure doesn't show us anything about stability. So we can eliminate that as an answer, okay? Resonance does not explain stability. And letter D says that the molecule contains 3 single bonds between our carbon atoms and 3 double bonds between carbon atoms. And that is incorrect because that's only looking at the picture. That's not actually thinking about what resonance means. And resonance means that they aren't single and double. It is an average between them. We just can't draw an average. So we'd eliminate letter D. So letter C is true because Again, they are an average. It's not a single or a double bond. It's somewhere in between, like a 1.5 bond. So all your bonds would have the same bond length. Okay, we're going to take a look at formal charge. This is an optional section because we don't see this pop up on the AP exam too often, but it is a nice topic to go over and something that can get you that maybe that one extra question on the AP exam if you know how to do it. So formal charge is used as a way to judge a structure of a chemical and determine if it's the best way to draw that structure. Most of the time we arrive at the best structure by following the octet rule. So doing our steps to draw it, following that octet rule, checking all our stuff. But sometimes that structure is not the best way to draw it, not optimal. So formal charge only needs to be used to evaluate structures when you're asked to do so or as a way to check your structure. So they would specifically say in the question, use formal charge to determine which of these is the best structure, something like that. So how do we calculate formal charge? Well, it's for each atom in the chemical. So it's its number of valence electrons minus the number of lone electrons on that atom in the structure minus the number of bonds on that atom in the structure. So let's take a look at just water and ammonia here as examples of how to calculate it. And then we'll see how it's used to evaluate other structures and see which one's the best. So I'm going to start with oxygen. So my formal charge on oxygen would be its number of valence electrons. So oxygens always have 6 valence electrons minus its number of lone electrons. So this oxygen has 2 lone pairs, so that's 4 lone electrons. So 4 dots basically. So it's valence electrons minus dots minus the number of bonds. Well, the oxygen has 2 bonds attached to it, so we get minus 2. So 6 minus 4 minus 2 gives us a formal charge of 0. All right, we're going to also calculate formal charge for hydrogen. Now the hydrogens both match, they're both bonded the same way, so we really only have to calculate it once. Well, hydrogen has 1 valence electron. Those hydrogens have 0 lone pairs because they should never have lone electrons. And then each hydrogen has 1 bond, and we get 0 for the formal charge. Getting 0 on our formal charge is the optimal number we can get. So getting 0 tells us that the electrons are distributed evenly in our chemical and in the best way we possibly can. So this is a good structure for water. Let's check out the NH3 as another example of how to calculate formal charge. So we're going to do the nitrogen. Nitrogen atoms have 5 valence electrons. In this structure, that nitrogen has 2 dots, or a lone pair. And that nitrogen has 3 bonds. So 5 minus 2 minus 3 gives us a formal charge of 0. And if you notice these 3 hydrogens that each have 1 bond still, they are the same as the hydrogens in the water molecule. So the same calculation would work for hydrogen. We'd still have 1 bond minus 0 lone electrons minus, 1 valence electron minus 0 dots minus 1 bond would give us 0 for hydrogen. So again, having a formal charge of 0 on each atom is optimal. That's what we want. That's why these structures are great and why all of our steps that we do to get to these structures are really good steps most of the time. Using that octet rule works most of the time, but we're going to see an example where that doesn't quite work. So formal charges of each atom are best when they are 0, but a +1 or a -1 formal charge is good as well. We don't want to get much past that. We don't want to get -2s or +2s or beyond. So if a chemical has larger formal charges, then we could we could argue that the electrons are not distributed in the optimum way, and we should look at another structure. We should look at moving some of the electrons to create a different structure. Typically, you will need to move lone pairs to make double or triple bonds to change the formal charge of the atoms. And so we're going to take a look at an example of this. We're going to try drawing sulfate, SO4 2-. We're going to use the rules we normally have done. Nothing crazy there. So sulfur has 6 valence electrons. Each oxygen has 6, and there's 4 oxygens there. And then we have 2 extra electrons from the charge. So we've got 6, 12, 18, 24, 32 electrons. So our sulfur, we're going to put in the middle. We're going to single bond those oxygens like we love to do. And that uses 8 electrons. So we have 24 left. And then we're going to add some lone pairs. So get our octets on our oxygens. So there's 6, 12, 18, and this one will give us 24. So that uses up all of our electrons, and we could do our brackets with our 2- charge. And we can look at that and say, hey, everybody's got their octet. We've used up all of our electrons. This looks like a great structure. I love it. Beautiful. Well, let's calculate our formal charge. So we're going to start with the sulfur. Sulfur has 6 valence electrons. We're going to subtract any lone pairs or any dots. It doesn't have any. And then we're going to subtract its bonds. And our sulfur gets a formal charge of +2. Our oxygen atoms, all of them are the same. They all have 6 valence electrons. They all have 6 dots. And they all have 1 bond. So in that case, we get a formal charge of -1. And we can see that this shows us that this is not the optimal structure for this. Sulfur doesn't have enough electrons on it. So we've seen already that sulfur can bond. It can have more than an octet. And this is a great example of where sulfur can get more than that octet and actually have a better structure. Okay, so if I want to reduce sulfur's charge, I want to make this closer to 0, then I need sulfur to get some more electrons. Now, the only thing we can do here is move some electrons. We've already used them all. So we can change some of our oxygen, and we can take a lone pair and share it with sulfur. Okay, if I did that, that creates a double bond there. So I'm just going to do a little recalculating. It still has 6 electrons, 6 valence electrons. But now the sulfur, it would still have 0 lone pairs, but it would have another bond. So instead of subtracting 4, we would subtract 5. And now we get a +1. So we're closer to 0. We want that central atom. We really want that thing to be a 0. That would be more optimal there. So what if we did it again? We take a lone pair, we move it. That gives us another bond, but doesn't change our dots or our valence electrons. It gives us another bond. And now our formal charge is 0. Okay, now I've changed 2 of the oxygens, right? 2 of my oxygens look like this one, and now 2 of my oxygens look different. So let's calculate their formal charge. So they still have 6 valence electrons. Those 2 oxygens, so I'm going to do a little sketch of this at the top so you can see, have a little clearer picture. So my top and bottom oxygen haven't changed, but my 2 on the sides have. Okay, so my 2 on the sides, I'm going to calculate their formal charge. So they got 6 valence electrons minus 4 dots for each one, minus 2 bonds. So now those lone pair, or those oxygens now have a formal charge of 0 as well. So we went from our sulfur having a formal charge of +2, and we've reduced that down to 0. And then 2 of our oxygens had a -1 formal charge, and now they're at 0. So 3 out of our 5 atoms have a formal charge of 0, and only 2 of them have a -1 formal charge. And guess what? We've added 2 electrons to this chemical, right? It's an ion. So having those 2 extra or having 2 of our oxygens have that -1 charge from those added electrons is perfectly fine and expected. So now we can imagine if I can have 2 double bonds on my sulfate ion, those two double bonds could be in more than one place, right? So we could make a structure like this with single, oops, oh my goodness, with single bonded oxygens on the sides, and of course you'd fill in all your electrons. We could do a structure that looked like this, where we had a double, single, single, double, something like that. So there's more than one option for this. It becomes a resonance structure at that point. So formal charge is really interesting because it does take this into a more depth and really has us look at what's the best structure we can possibly draw for something. So how does this look on the AP test? What are some other examples? So here's a good example of what they might give you. They say, which of the following is the best diagram for N2O considering formal charge? So what does that mean? It means we need to calculate the formal charge on these elements, on these atoms, and then see which one has the lowest formal charges. Okay, so for each one, we've got a nitrogen, and an oxygen. So I'm going to do each of those. So our first chemical, our nitrogens have 5 valence electrons. That's not going to change. My first nitrogen over here is what I'm going to start with. So that minus its lone pairs, or its lone dots, it's got 4 dots, minus its bonds, 2, would give us a -1 formal charge. Our nitrogen in the middle would be 5 valence electrons minus 0 dots minus 4 bonds, gives us a +1 formal charge, and our oxygen has 6 valence electrons minus 4 dots minus 2 bonds, gives us a formal charge of 0. Whew. Okay, I'm going to do the next one in a different color so we can make sure we're differentiating. So nitrogen, oxygen. Nitrogen, that first number is never going to change for our elements. All right, our first nitrogen on the left has 2 dots and 3 bonds, so that gives it a formal charge of 0. Nitrogen in the middle has 0 dots and 4 bonds, so that's a -1. And our oxygen has 6 dots and 1 bond, so -1. So far these two are getting pretty close to each other. All right, our next one, we've got nitrogen, oxygen. 5, 5, 6, those don't change. So nitrogen on the left has 6 dots minus a bond. That is 5 minus 6 is -1. That's -2. All right, just based on that alone, I know I'm going to eliminate option C because I'm already at a -2. That is not optimal. That's not a best diagram if I'm getting to -2. So I'm going to eliminate that one, and I'm going to go to my last one. This one has nitrogen, oxygen, nitrogen, so that's a little different. So we got 5, 6, and 5. So nitrogen on the left has 6 dots and 1 bond. That gives me a -2 again. I'm eliminating that one. So we've eliminated 2 options already because they got a formal charge of -2. Now we want to look at these other 2 structures and see what's our best option here. So as we are down to these last 2 options, we want to pick the structure that has our formal charge, our negative formal charge, on the most electronegative atom. So negative formal charge on most electronegative atom. So having that negative formal charge on our most electronegative atom makes sense because we want the atom that's going to attract the electrons the most to have that negative charge. So if we look at our 2 options, our oxygen in the first one has 0 as its formal charge. Our oxygen in the second one has -1 as its formal charge. So that is our best option. So looking at these structures and comparing them, we can see the one on the letter B has that triple bond for one of our nitrogens, which they prefer. Can't satisfy it for both, but at least for one. And again, puts that extra electron, that negative charge, on the oxygen at the end. All right, here's another example. So which structure minimizes formal charge for each element? So we want to see which structure is the best one to get our formal charges to the lowest value possible. Something I like to look for is elements that are similar between all of the chemicals that are bonded the same way. For instance, we notice each fluorine has 3 lone pairs in a bond. So if we calculate our formal charge for fluorine, they're all going to be the same. They all have 7 valence electrons. They all subtract 6 dots and 1 bond. So all of our fluorines are 0. So I wouldn't worry too much about fluorine. What is changing here is the selenium and the oxygen. So we have double bonded oxygens, we have single bonded oxygens. So, and then we have 3 different forms of selenium. So over here, I'm going to look at my double bonded oxygens first because they're very similar to each other. So a double bonded oxygen, all oxygens have 6 valence electrons. If they're one of the double bonded oxygens, they have 4 dots and they have 2 bonds. So that gives us a formal charge of 0. So double bonds are pretty great for oxygen. If we have the single bonded oxygen, so these are both oxygen, then we have 6 valence electrons. They're going to subtract 6 lone pairs, or excuse me, 6 dots, and 1 bond. So we're going to get a formal charge of -1. So not as optimal, but still in a good range. Now we have 3 forms of selenium. So I'm going to do the selenium for each one of these different structures. So for structure A, we've got selenium has 6 valence electrons. And for this first one has 0 lone pairs, 0 dots, minus 6 bonds. So that gives it a formal charge of 0. Letter B for selenium has 6 valence electrons, minus 0 dots, minus 5 bonds. So we get a -1. And for the last one, we get 6 valence electrons, minus 0 dots, minus only 4 bonds. So we get a +2. This should be +1, sorry about that. So right now, our structure that we can definitely eliminate would be C, because it has that +2 there. It also has single bonded oxygens, and they have a -1, and then the fluorines are all the same. So that's definitely not optimal. But if we look at structure A, it has a selenium that's 0, it has fluorine that's 0, and it has double bonded oxygens that are 0. So picture A, or structure A, would minimize our formal charge for each element. It gets all of them down to a formal charge of 0. So even though letter C follows the octet rule and gives selenium only an octet, letter A is actually better. Giving selenium more than an octet satisfies our formal charge more and gets it down to 0. So that is a better structure for this chemical than letter C or B are. So you might go ahead and pause this, try this example, and then we can do it together. So we've got 2 structures for carbon dioxide, and we want to explain in terms of formal charge why diagram Z is a better diagram. So try at least calculating your formal charge for each element. If you get stuck on the explaining, we can go over it, but let's check it out. Okay, so if we start by just calculating our formal charge. So for a diagram X on the left, we've got our carbon in the middle. I always like to start with my central atom. So our carbon in the middle, it has 4 valence electrons, minus 0 dots, minus 4 bonds, has a formal charge at 0. Our oxygen on the left side has 6 valence electrons, minus 6 dots, minus 1 bond, so that would be -1. And our oxygen on the right side has 6 valence electrons, minus 2 dots, minus 3 bonds, so 6 minus 5 gives us +1. So we've got formal charges. We've got carbon as a 0, but each oxygen is different, which is kind of awkward, and one's negative, one's positive. If we look at the other diagram, then we've got our carbon in the middle, 4 valence electrons minus 0 dots minus 4 bonds gives us a formal charge of 0. So the carbons are equal in their formal charge, but the oxygens here are both the same, which is nice. They have 6 valence electrons minus 4 dots minus 2 bonds, which gives us a formal charge of 0. So both of them being 0 is optimal. So that's why we like diagram Z, but we need to explain why. So Z has all elements or all atoms with a, it's better to spell that out, with a formal charge of 0. This makes it the optimal structure because it means all electrons are distributed more evenly between atoms. So that's how we could use our formal charge to help explain why a particular structure is better than another one. So these examples here are types of questions that have been on the AP test. I pulled those from the College Board site so you can get an idea of how formal charge might be used on the test. Typically, they're going to give you structures to analyze, and you're going to find the formal charge of your elements and then either pick a diagram or explain why a diagram is better than another one. Outside of that, we really don't see formal charge used that much in AP chemistry. So let me know if you have questions, and I will be more than happy to help you out. Thanks, guys.